through this talk, you will see that this is actually an important question that we have to ask ourselves. And what I'm trying to do with this presentation here is to show how changes in tides can affect flooding along the United States coastline. When we think about tides, the daily up and down of the water level when we go to the beach, the tides come in and they go out twice a day, once a day, depending on where we are on the planet. And those are predictable. And for a very long time, we have assumed that these tides are stationary, that they are not changing over time. And that assumption makes sense because they are, at the end, driven by the sun, moon, and earth system. And that system doesn't change much. Otherwise, we would have much bigger problems. But tides are also just long waves. And that means that locally, they can change quite a bit for many different reasons. And just a few of them are listed here. And the most important one is dredging. If we want to bring in big ships into our ports, which are often located in urbanized estuaries, we need to dig channels and then maintain the channel depth for these ships to come in and go out. And that changes the bottom friction, and that can lead to significant changes in how tides propagate in and out of these estuaries, which can then lead to a change in the tidal range, the difference between the tidal high water and the tidal low water. Other reasons can be land reclamation. We can have changes in turbulence because we are building dikes, piers, jetties, and so on. And sea level rise can also affect tides. If sea level rises quite a bit, that also has an effect on bottom friction and how these tidal waves propagate along our coasts. Research has shown that past sea level rise probably had a relatively small effect on changes in tides, but going forward, depending on how much sea level is going to rise throughout the century, we might see more significant changes. And there were some two excellent review papers actually published last year, one by Ivan Haig and colleagues, and another one by Stefan Talki and David J., where they discuss in great detail the many reasons why tides can change, where they have changed in the past. So I encourage you to look up those papers if you're interested in this topic. Also along the US coast, we know that nuisance flooding or sunny day flooding or high tide flooding is really becoming a big issue, especially along the US East Coast, but also other places around the globe and also the West Coast of the United States and the Gulf Coast, of course. And the frequencies of these nuisance flooding events are increasing due to sea level rise. And because we expect sea level rise to accelerate moving forward, we also expect the event frequencies of these nuisance flooding instances to increase and accelerate in the future. Now, these nuisance flooding events, as the name indicates, they are not killing anyone. They don't severely injure people, but they can significantly disrupt our daily lives because businesses cannot open, transportation infrastructure is affected, roads have to be closed. And if that happens on a pretty regular basis, then the impacts of these minor flooding events, if accumulated, can actually be more relevant and more important than the impacts that we see from very extreme but also very rare events, such as landfalling tropical cyclones or hurricanes that cause extreme storm surges, but that only happens every 10, 20, 30, 50 years, depending on where you are. And what we tried to do here in this analysis or with this research that we conducted is that we tried to link the changes in tides to the changes in the event frequencies when it comes to nuisance flooding. And we actually followed a pretty simple approach to do that. And I'm trying to walk you through that now step by step. We are using here Wilmington as an example, and we use tide gauge data, hourly water level observations from tide gauges for our analysis. And that is the tide gauge of Wilmington in North Carolina here. And from this tide gauge, we have hourly observed water levels, which is the blue time series here in this graph. When we have this water level time series, what we can do is we can apply a harmonic analysis to extract the tidal signal from these observed water levels. And the tidal signal, that is the predictable part, the deterministic part of the water level. And then we have stochastic components on top of that that are driven by wind and pressure, which are, of course, not as easy to predict. And And luckily, in our study, we had a colleague involved, Stefan Tarki, who has done a lot of data rescue and data archaeology work over the last 10, 20 years. He rescued a lot of historic tide gauge records and digitized them and made them available to us for this analysis. And that is why we have data here from around 1910. And we use this water level data from early in this record, perform a tidal analysis, a harmonic analysis, to identify what the tides looked like 100 years ago, in this case, in Wilmington. And we refer to this as the historic tidal conditions. We then perform the same tidal analysis every year moving forward through our data set using this blue time series, the observed water level from the tide gauge. And for each year, we obtain tidal constituents, so slightly different tidal conditions, because we do it on a year-by-year basis. We allow the tides to change over time. And that is something that definitely happened here in Wilmington. As you can see, the difference between high and low water is increasing over time, which is the result of an increase in the tidal range. So now we have an observed tide, we call it the observed tide, that is changing over time. And we remove that from the observed water level, and we replace it with the historic tide, assuming that there were no human alterations to the system and the tides would still be the same as they were 100 years ago. So what we do is we turn this blue time series that we see here into the red time series, which then includes the historic, assumed, unchanged tidal conditions. And the black horizontal line, that is the minor flooding threshold that is defined by the National Weather Service in Wilmington. And when that threshold is exceeded, we assume that there are at least some flooding impacts somewhere in the area. And we can see that, of course, this blue time series crosses this threshold way more often than the red time series. And this is what we do here. We compare the observed water level and how often this observed water level exceeds the threshold with the number of threshold exceedances if we assume that the tides have not changed. And then we can compare these two numbers and we can find out how many additional nuisance flooding events have we seen over the last few decades because of changes in the tides. And we did that for a total of 40 tide gauge locations along the US coastline. Many of them are located in estuaries, which are shown here by triangles. Others are located along the open coast, which are shown by circles. Red color here denotes that we have more nuisance flooding events because of changes in tides, which means the tidal range is increasing, similar to what we saw in Wilmington. And you can see here Wilmington is dark red. But we can see many other places where we have red color, which means there are many other places where we have seen more nuisance flooding over the last 50, 60 years or so because of changes in the tides. We also have few locations where we see blue color, which means that we had a decrease in the tidal range. And that means that these tidal changes actually helped offsetting some of the impacts of sea level rise by leading to less nuisance flooding that we would have otherwise seen. And when we look at individual stations and we do it on a year by year, instead of looking at the aggregated data that was shown on the previous slide, we can see that most of these additional nuisance flooding events that we have observed and that occurred in the past because of changes in the tides actually happened over the last few decades, the last 10, 20, or 30 years. And that is because if we go back early in time, the gap between the high tide level and our flooding threshold was pretty large. We didn't have nuisance flooding. When I started my career working on that stuff 10 years ago or so, there was no term for this kind of phenomenon. Now we have nuisance flooding, high tide flooding, sunny day flooding, minor flooding. So there are at least 4 terms now to describe this phenomenon. And now we are in this period where the gap between the high tide level and the flooding level is really small. And that means that these additional changes in the tides that we have seen in the past actually now lead to more or less nuisance flooding in many places. And if we move forward with enough sea level rise, at some point, almost every high tide would exceed the threshold, and then these tidal changes again become less important. And what we then did is we took this data that we created here and we aggregated it in different ways. First, what we did is we took all the locations where we found a positive change in nuisance flooding. Positive meaning we have more nuisance flooding, so from an impact perspective, it's actually bad. And we can see here that up to 30% of the observed nuisance flooding events over the last couple of years only occurred because the tides have changed over time. Sea level rise is still the main driver for this increase in nuisance flood frequencies, but changes in tides in many places also played an important role. And negative changes, places where we see less nuisance flooding, if we aggregate that data, we can see that the effect is actually much smaller. If we look at estuarine locations versus coastal locations, we find that the majority of the changes take place in estuaries. And that refers back to my title and what I mentioned at the beginning. If we want to bring in big ships into our ports, we need to dredge the channels, and that happens in these urbanized estuaries, and these systems are very sensitive, and that can lead to significant changes in the tidal range. And that can increase the flood risk quite a bit, depending on how much the channels have been deepened. If we separate the east and west coast, we find that the changes are more extreme on the east coast, which is where we also see more nuisance flooding to begin with. This gap between the high tide level and the flooding threshold is a little bit smaller compared to the west coast, and also many of these urbanized estuaries that have been affected are located along the east coast. The last part here, I don't want to go into details, but in addition to these daily high and low tides that we observe when we go to the beach, there are also longer period tidal signals, the perigean cycle and the nodal cycle, which has a period of 18.6 years. And there was a really nice paper published 2 weeks ago in Nature Climate Change by Phil Thompson and colleagues, where they look at future projections of high tide flooding, and they show how this nodal cycle is really important to cause periods where we see a lot more of an increase in nuisance flooding frequencies as compared to other periods. And that actually went viral. The media picked up the term the moon wobble, and it's all over the news now. And what it really means is that this nodal cycle plays an important role also in modulating nuisance flooding events. And what we show here is basically the same thing, that if we have a relatively small gap between the high tide level and the flooding threshold, which we do have right now, then these cycles, these 4.4 and 18.6 year tidal cycles, are actually quite important in causing more or less nuisance flooding during certain time periods. The last thing that we looked at is more of a time scale perspective. So far, we have counted events, incidences of nuisance flooding in the past, and we compared how many did we see and how many could we have seen if the tides hadn't changed. Whereas here we are looking at how long does it take for us to see a certain amount of nuisance flooding events per year. And we picked pretty randomly here 100 events. So we asked ourselves, how long does it take under different sea level rise scenarios? We have a high, intermediate low scenario here that we are looking at. We asked ourselves, how long does it take to reach 100 nuisance flooding events? And then what we did is we looked at the distribution of the daily high water levels for San Francisco, for example, here in red. And if we take the data, the historic data from 100, 150 years ago, we get this solid red line. So this is our daily high water distribution. If we take the data from 2019, which is the last year from where we have complete data, we see the distribution is shifted to the right. So that indicates that in San Francisco, there was an increase in the tidal range. The high tide or the daily high water level has increased, not just because of sea level rise, but also because of changes in the tides. Washington, D.C. is an example where if we take the historic data, we can see, again, the solid blue line here, and compare it to the modern data is shifted to the left. So Washington, D.C. is an example where we actually had a decrease in tidal range, which, as I mentioned before, is a good thing from a nuisance flooding perspective, because we have seen less nuisance flooding events because of these changes in the tides. Now, these vertical lines, those are the flooding thresholds for these two locations, for San Francisco and Washington, D.C. And the horizontal line, this just represents 100 nuisance flooding events per year. Now, what happens with sea level rise is that these distributions shift to the right. And at some point, these distributions will intersect with this point here, where we already see the intersection of the flooding threshold and 100 nuisance flooding events. And that takes a certain amount of sea level rise, and that takes a certain amount of time. So what we did is we looked at how long does it take to reach this point when we assume present-day tidal conditions, and how long would it take to reach this point if we assume historic tidal conditions. And then we can compare these two time periods. So it may happen, for example, in 2050 with the modern data, and it may happen in 2040 with the historic data. That means we have a difference of 10 years. And that difference is what we are looking at here in the other three panels for the different sea level rise scenarios. And if we look at a high sea level rise scenario, sea level rise is really quick. So we will pass through this distribution relatively quickly, and these differences are not as important. However, if we follow an intermediate or even an intermediate low sea level rise scenario, then these time differences become larger, and we actually lose time to prepare for this event where we now see 100 nuisance flooding days per year. We can do the same analysis for 50 events or 20 events, but what it shows is that because of these changes in the tides that took place in the past, we lost adaptation time to prepare ourselves and our communities for these high tide flooding events. And you can see here, in some cases, we actually lose 20, 30, or even in an extreme case in Wilmington, up to 50 years. So we now see 100 nuisance flooding events 50 years earlier, just because of the changes in the tides that took place in the past, and are oftentimes easy to trace back to anthropogenic impacts. All right, a few take-home messages from me as well. The first one is that tidal characteristics have changed in many places. Tides are not as stationary as we assumed for a long time, and that has a significant effect on nuisance flood frequencies. The effects are strongest in urbanized estuaries, where the changes, as I mentioned, can often be traced back to anthropogenic impacts, channel deepening, dredging. The tidal changes on top of sea level rise, and that's what we saw on this last slide, can reduce our time windows for adaptation if we want to avoid crossing these critical frequency thresholds like 100 events per year, 50 events per year, 20 events per year. It really depends on how much you are willing to accept. And a very important message is that our analysis here, we were very data hungry, so we needed long tide gauge records to perform this analysis. So that restricted us to a certain number of locations, 40 in total. But it's very likely that similar changes have taken place elsewhere and have gone unnoticed because we don't have the data available yet. And the reference for the paper where all this is described in more detail is here at the bottom. And as I mentioned before, Sida Li, a visiting student from China, is really the one who takes the credit for this work. And I will stop here and answer any questions that you may have. Thank you very much.